let's imagine that we have 250 grams of water. And it is at 20 degrees centigrade, 20 degrees centigrade. We add to it an amount of heat of, let's say, 1 times 10 to the 4th joules. The question is, what is the final temperature of the water? Well, we know that delta T, well, let's write it first. We know Q equals mc delta T. So delta T will equal Q over mc. So Q is 1.00 times 10 to the 4th joules divided by the mass. The mass is 250 grams, but let's make sure we write it in standard SI units. So kilograms, 0.250 kilograms, times C, the specific heat of water. Now actually I said that it requires 1 calorie to increase the temperature of 1 gram of water 1 degree Celsius. So it turns out then that for 1 kilogram, that would be 1,000 calories, 4.186 joules per calorie, or 4,186 joules per kilogram degrees Celsius. So that is the specific heat of water, 4,186 joules per kilogram degrees Celsius. Divide that out, and what we find is that delta T is 9.56 degrees Celsius. So what's our final temperature? 20.0 plus 9.56 degrees Celsius, or a final temperature of 29.6 degrees Celsius. So there's our final temperature. All right, now let's try another one. Now we're going to take a look at a different kind of calculation. This is called a calorimetry experiment, or a calorimetry experiment, calorimetry calculation. So let's imagine, and this will be similar to something we'll actually do in lab. Let's imagine that we have some water, again. So let's imagine we have 3 kilograms of water, okay, H2O, at 20 degrees Celsius. 20 degrees Celsius corresponds to just about room temperature, so it's a common initial temperature to start with for something. Let's imagine we've got a block of some material. Maybe this is copper. And let's imagine that we have 1 kilogram of copper. What we're actually going to do in lab, and this is a common kind of experiment, is to heat up your material. And so that you know what the initial temperature of the material is, imagine that you put it in some boiling water and you let it sit in the boiling water for quite a while. Well, you know water, if it's boiling, is at 100 degrees Celsius. If you let this sit in there for quite a while until it comes up to an equilibrium temperature with the water, then we can assume that its temperature is 100 degrees Celsius. So let's imagine our initial temperature for the copper is 100 degrees Celsius. We put that copper into the water. Now what's going to happen? Well, the hot copper is going to heat up the water. The cooler water is going to cool down the copper until we'll end up with the water and the copper at some final equilibrium temperature. We'll call it T sub F. The question is, what is T sub F? Let's assume that we know what the specific heat capacity of water is, and let's imagine we know what the specific heat capacity of copper is, and it is 387 joules per kilogram degrees Celsius. So knowing that, let's see if we can't figure out what is the final temperature of our copper and water. Now the idea is we're going to assume that the water gains energy from the copper loses energy, and we'll assume that we don't lose any energy to the environment. So we're going to assume conservation of energy so that whatever energy is exchanged goes from the copper to the water, but without any going into the environment or coming from the environment. So we'll have some energy change for the copper, some energy change for the water, Now, if the energy change of the copper is negative, the energy change for the water will be positive. So the copper is losing energy, the water is gaining energy. The sum of these we then expect to be 0. So the fact that this is 0 means nothing is going to or coming from the environment. All right, so what's Q of copper? We know Q equals mc delta T. So Q for copper will be mass of the copper, C of the copper, delta T of the copper, and then Q of the water will be mass of the water, C of the water, delta T of the water, and we know the sum of these must be 0. So in other words, we know M and C are both positive quantities, so in order for the sum of these to be 0, one's going to have to be negative. In other words, delta T copper or delta T water, one will be positive and one will be negative. Well, what do we expect? We expect the water to heat up, so we expect delta T water to be positive. We know the copper is going to cool down, so we expect delta T copper to be negative. And that's going to give us then a positive and a negative quantity, which we expect to add to 0. All right, so let's put some numbers in here. We have mass of the copper, which is 1 kilogram, times specific heat of the copper, which is 387 joules per kilogram degree Celsius, times delta T of the copper. Now, delta of anything is always the final minus the initial of that quantity. So delta T of the copper will be the final temperature of the copper, which is TF, that's the final temperature of both the copper and the water, minus the initial temperature of the copper, which we know is 100 degrees Celsius, plus mass of the water, which is 3 kilograms, times specific heat of the water, which we know is 4,186 joules per kilogram degree Celsius, times the temperature change of the water, which is the final temperature of the water, which is also TF, minus the initial temperature of the water, which is 20 degrees Celsius. And we know all of that must equal 0. So what do we find? Let's multiply this out. We have 1 times 387 times TF, so that gives us 387. Now notice kilograms cancel. We'll have joules TF per degree Celsius. And then that quantity times 100 minus, so minus 387, 38,700. Notice that we'll have now the degrees Celsius canceling the degrees Celsius, leaving us with joules. And then we'll have 3 times 4186, so we have plus, 1.26 times 10 to the 4th. Notice the kilograms cancel. We'll have joules temperature final per degree Celsius. And then minus that quantity times 20, that is 2.51, times 10 to the 5th. And again, the degrees Celsius will cancel and we'll end up with joules. And all of that equals 0. All right, so notice we've got TF and a TF term here, and a joule term and a joule term here. These are negative. Let's take these and stick them over onto the other side. And what do we end up with? Combine this one and that one, and we get 1.30 times 10 to the 4th joules TF per degree Celsius. And that equals, and let's take this one and that one and put it on the other side, and what do we get? 2.90 times 10 to the 5th joules. Multiply both sides by degrees Celsius, divide off the joules from both sides, divide by 1.3 times 10 to the 4th, and we find TF is equal to 22.3 degrees Celsius. And there is our final answer. Now, let's think, does that make sense? Well, first of all, 22.3 degrees is warmer than 20, so yeah, the water has heated up. It's less than 100, so yes, the copper is cooled down. However, it's a whole lot closer to 20 than it is to 100. Now, does that make sense? Well, yeah. First of all, we've got 3 times as much water as copper, 3 times the mass, so we expect the temperature of the water to change less than that of the copper. Also, the specific heat of the water, remember, is 4,186, while that of the copper is only 387. The specific heat of the water is more than 10 times that of the copper. So we expect the temperature of the water again to change much, much less than that of the copper. So the water only heats up by 2.3 degrees, while the copper cools down by almost 80 degrees. So we get a much larger change in the copper than that of the water. All right, very, very good. We will continue with this, our looking at temperature and the way heat affects things, next time, and we will look at some more complicated calorimetry type experiments.